All right, so welcome back. This is our last topic here in Unit 9, talking about solving systems of nonlinear equations. So a nonlinear system is one where you have one or more equations that are nonlinear terms, typically dealing with conic equations. So circles, parabolas, ellipses, hyperbolas with a linear equation or multiple conics intersecting each other. So because we're talking about the intersections, there's a certain type of number of solutions you could be generating for this. So a linear quadratic system, shown very nicely right here, found a nice online graphic for this, shows two solutions, one solution, or no solutions based on how the lines intersect. So a linear line with a parabola is illustrated right here. This same applies to a linear line with hyperbola, with a ellipse, or even with a circle. All right, so I'll show an example of one of each type, 0, 1, and 2 solutions. So typically with the linear quadratic systems, your best bet is to use the substitution strategy. Take the linear equation, solve for either x or y, whichever one you find easiest, and then substitute that into the quadratic portion of the system. The matrixy methods will not apply to this right here based on our current knowledge, so it has to either be elimination or substitution. Elimination is not really going to work out because we really can't eliminate a variable term if we've got a squared term in one equation but no squared term in the other. So the linear equation, I'm probably going to isolate y first by adding x and subtracting 3. So y equals x minus 3. So I go ahead and fill that into the quadratic. We still have 5x squared, but it's minus 4 times x minus 3 squared minus 25x plus 2 times x minus 3, and then plus 30. So we get 5x squared. This will FOIL out to be x squared minus 6x plus 9. We distribute both those expressions. We're going to get a negative 4x squared plus 24x minus 36. And on the other side, a plus 2x minus 6. So combining our like terms, 5x squared and negative 4x squared make a positive x squared. 24x, negative 25x, and positive 2x make a 1x. And then negative 36, negative 6, and positive 30 make a negative 12. All right, so we have this quadratic, which can factor as x plus 4 and x minus 3, giving us two x answers. So this is where we get our two solution possibility. X is negative 4 and x is positive 3. So the y values that correspond, when x is negative 4, y is going to be a negative 7. When x is 3, y is going to be a 0. So your two answers are negative 4, negative 7, and 0, 3. So if you were to graph these two, obviously linear, and then the top is a parabola, hyperbola, because it's x squared minus y squared, you would find they'd intersect in those two spots, negative 4, negative 7, and 0, negative 3. So that's what it looks like to be a 2 solution. So we have 0 and 1 solutions left. Here we have another hyperbola in linear line. This one, it's clear that solving for y is your best choice because the x has a coefficient. So y is going to equal negative 2x plus 4. And we're going to fill that in for our y term in the problem, negative 2x plus 4 being squared. And then 5 times that negative 2x plus 4 here, minus 85 equals 0. So squaring it first, we're getting 4x squared minus 16x plus 16. And then we have our plus 5, negative 2x plus 4, minus the 85. Distributing is going to give us a negative 12x squared plus 48x minus 48 minus 14x minus 10x plus 20 minus 85. When we go through and combine our like terms, we're going to get a negative 9x squared for the x terms. When we go ahead and combine our regular x's, we have 48 and negative 14 and negative 10. That's going to make a positive 24x. And then we have our negative 48, positive 20, and negative 85, giving us a negative 113. Now, we talked about there could be 0 solutions. This would be kind of like a dead giveaway. This is going to be a 0 solution situation because all your answers for our problem is going to work out nicely. So if there's a coefficient in front of x squared, it's probably not. Now, if that 9 could divide into everything, then we'd be able to, but we can only divide, I can't divide anything at all. So the way we confirm that this is a true no solution is because we remember your quadratic formula solves every single quadratic no matter how simple or complicated it is. And your quadratic formula has this thing called the discriminant, the b squared minus 4ac parts. So if we were to calculate our discriminant for this equation, and if that comes out to be a 0, then we know that this is a no solution because this can't actually solve that because it creates imaginary answers. So our discriminant, b squared, would be 24 squared minus our 4 times negative 9 times negative 113. 24 squared is 576. Negative 4 times negative 9 times negative 113 is negative 4,068. And when we do 576 minus that 4,068, we get a clear negative number. So that tells us we have a negative inside, so this is our no solution answer. All right, so you'll be able to speculate that's no solution because of the coefficient in front of the x squared or the y squared, whatever was left over there when trying to solve it, because they have to be integer answers for everything that we do, and everything you'll be seeing here. But you can confirm it by finding your discriminants and confirming that gives you a negative value. All right, so that's our no solution. So this last one's our one solution. Let's solve for x this time, just so you can kind of see me solving for y. It doesn't really change the overall process. It's just a different variable to plug into it. So this is with a circle and a linear line. So we go ahead and substitute the negative y minus 3 in for x. So we go ahead and square that, getting y squared plus a 6y plus a 9. And then negative 8y minus 24, 2y and 15. We combine to get 2y squared. The y squared's there. 6, negative 8, and 2 make a 0, so the y terms completely cancel. And then 9, 15, and negative 24 also cancel. So we get 2y squared equals 0, which means y is 0. And plugging that back in, we get x to be negative 3, and there's our one answer. So it's not saying that you have to get a 0 to be the one solution situation. That's not what it's saying in the slightest. It could have yielded a quadratic that was a perfect square expression. So like y squared plus 4y plus 4 would just be y plus 2 squared, so there's only one answer from that resulting quadratic. But that is an example of what it could look like. So those are our linear quadratic systems, 0, 1, and 2 solutions. We also could have the intersection of quadratics. Now, I couldn't find a nice graphic for that, so I just kind of hand drew a couple different scenarios here. So obviously we have 0 solution, 2 parabolas not intersecting. 1 solution, the ellipse and a parabola intersect exactly 1 time. 2 solutions showing 2 parabolas intersecting. 3, a parabola intersecting through a ellipse there. And then finally 2 ellipses intersecting, creating the 4. So there's 5 different possibilities here based on these different setups. And we're going to go through each one of those 5 so you can kind of see an example of how that's going to play out. Now for these problems, so the linear quadratic was substitution based for your solving. Quadratic are going to be based on using elimination. And recognizing right off the bat, the x squareds have the exact same coefficient, just one is they're both positive. So if I subtract these two equations, x squared minus x squared cancels. I get negative 3y squared. The 12 minus the 54 gives us a negative 42y. And the negative 78 minus 69 gives us a negative 147. Unlike that no solution from a couple examples ago, everything here divides by negative 3. The negative 147 and the negative 42 all divide with the negative 3. So we divide everything by the negative 3 to cancel, and we get y squared plus 14y plus 49 equals 0, which is y plus 7 squared. So we only get one answer for that y value. So there could be a one solution situation, that could be this, or there could be two, because when we plug this back in, there's still an x squared. There could be two x values that yield from the single y value right here. It's your choice which sub-equation to plug into. Let's just go to the top. So we get x squared plus 2 times negative 7 squared plus 12 times negative 7 minus 78 equal to 0. 7 squared is 49 times 2 is a 98. We get a negative 84 for the 12 times 7 bits. And then obviously we have the negative 78 there at the end. So 98 minus 84 minus 78 is a negative 64. So we're going to get two values for x, a positive and a negative 8. So those are two solution scenario. We have 8 comma negative 7 and the negative 8 comma negative 7 when these two ellipses intersect each other. So in terms of like a graph, this would probably look kind of like this right here. You'd have one ellipse and like a second ellipse kind of goes at it like that. All right, so again, elimination is going to be the name of the game for each and every one of these problems. It's going to be set up in a way that eliminates a term pretty quickly. Like you're noticing right here, the x's will both cancel when I add together because I have positive x squared, positive 8x, negative 8x. They're set up in that way so they eliminate pretty quickly because the problems by themselves can get rather complicated if they don't really eliminate quickly there because we have to get rid of all of one variable. So the x terms or the y terms have to kind of group together either immediately or in a way that they're common multiples of each other so they can eliminate pretty quickly right off the bat. So they are generally set up in a way that they're the same coefficients immediately to get rid of the x's or the y's in the problem. So we get 15y squared, we'll get a positive 45y, and then a positive 30 when we add them together. Again, there's a number in front of the y squared, but it divides into everything. Y squared plus 3y plus 2. This factors for two y answers, y plus 2 and y plus 1, giving us negative 2 and negative 1. So this will probably yield a 3 or 4 solution set, because when I plug in negative 2, I'm going to have an x squared in there. It could be one answer from that, or it could be two answers from that, and same thing with the negative 1. So let's do the negative 2 first. So we'd have x squared plus 8x minus 3 times negative 2 plus 9 equals 0. I find it easier to plug into this top equation in this particular scenario because there's only one y term to plug into, and it's generally smaller numbers in the problem as well. So x squared plus 8x, that will be a plus 6. Plus 9 is plus 15. So this yields two x answers. X plus 5 and x plus 3 are the factors. Therefore, negative 5 and negative 3 are the x answers. So we would have negative 5 comma negative 2 and negative 3 negative 2 for 2 points of intersection. The next y value is negative 1. So same equation up top, x squared plus 8x minus 3 times negative 1 plus 9. We're going to get x squared plus 8x plus 12, which factors as x plus 6 and x plus 2. So we get x equals negative 6 and negative 2. So those two answers would yield us a negative 6, negative 1, and then a negative 2, negative 1. So this is a 4-solution system here. We can see this is the scenario of having a parabola and a hyperbola intersecting, and it's hitting it 4 times if we were to actually graph out this entire thing. So yeah, theoretically, you could solve these systems by graphing. Not really the most efficient strategy without the aid of a computer program, but it certainly could be done. All right. Even so, again, if you were worrying about like, oh my goodness, 4 solutions can be so complicated, it's going to be so long, it really isn't that bad. The elimination works out pretty quickly, and you're just solving a bunch of quadratics. That's all it is. So as long as you can factor, you're good. If you're still struggling with factoring at this point, you really need to refer back to the Unit 2 video on that and get a little more comfortable with your factoring process. All right, so here we can see, again, elimination is your best bet. X's are going to subtract out completely. The x's are not going to subtract out. The y and the x squared will subtract out because 2 minus 2 is 0, but negative 10 minus negative 20 is a positive 10x. Y minus y is 0, and then we get minus 50 here. So that tells us 10x equals 50 and x equals 5. So it's not going to obviously always be the x values that cancel out. And this is going to be the one solution problem because there's only a y term in there. There's no y squared, so there's no way to get 2 possible answers. It doesn't really matter which one we plug into. Let's just do the top one. So 2 times 5 squared minus 10 times 5 plus y minus 3. We get 50 minus 50 plus y minus 3. So the 50s would cancel each other. Add the 3 over y is 3. We get 5 comma 3 for that particular answer. So that's what our one solution looks like. All right, so we've done a 2, a 4, and a 1. We still have the no and the 3 left to explore. All right, so looking to see what elimination is going to happen here. It looks like the x's will cancel when I subtract, because the x terms have the exact same coefficients, sign, and everything. So we go ahead and subtract. We get a positive 12y squared for the negative 1 minus negative 13. We get a positive 48y for the negative 5 minus the negative 53. And then we get a positive 76 for the 56 minus the negative 20. You're obviously also fully welcome to switch all the signs in the problem if you'd rather deal with an addition rather than doing your subtraction with negatives. Now, the 12 doesn't divide into everything nicely here. We can divide everything by a 4, though, if you want. But the 12 won't divide into everything nicely, which then should be your dead giveaway that this is going to be your no solution scenario. We confirm that with our discriminant, though. B squared minus 4ac. So 12 squared minus 4 times 3 times 19. We get 144. 4 times 3 times 19 is 228. So the 144 minus the 228 is a negative 84. So that confirms this is our no solution problem. And the reason why it's important to confirm that is because while I keep on talking about for our class, you're going to only have nice integer values. That does not necessarily mean that's the case for all future classes. So you want to always confirm that it's not a quadratic that still does factor but yields fraction answers. You want to confirm the discriminant really is a negative value each and every time. All right, so that's our no solution. So last up is our 3 solution. As we can see here, we can add. That'll cancel all the x terms, so that gives us 3y squared, negative 6y, and then the 52 plus the negative 76 gives us a negative 24. I divide the 3 into everything, and then I factor, and we get y equals 4 and negative 2 for our 2 solutions. Top equation is probably the easiest to work with. There's only one y term to substitute into. So we'll do that for the y equals 4. So we have 6x squared plus 36x minus 4 plus 52 equals 0. So that becomes a 48. A 6 does divide into everything. X squared plus 6x plus 8. So we get 2x values out of that, negative 4 and negative 2. So 2 answers. We would have negative 4 comma 4 and negative 2 comma 4 for the 2 points of intersection. So lastly, we have our negative 2 answer for y to plug in. So we'd have 6x squared plus 36x plus 2, because it's minus a negative 2. That yields 6x squared plus 36x plus 54. Dividing everything by 6, x squared plus 6x plus 9. This is why it's only 3 solutions, because that's a double root equation. X squared plus 6x plus 9 is x plus 3 squared, yielding just x equals negative 3. So our third answer is going to be the negative 3 comma negative 2. Okay, so those are your quadratic systems. That's the idea of solving your nonlinear systems. As I said numerous times, for our purposes, they will get all nice integer values. So if you do get that quadratic at the end that has a number in front of the squared term, you can't factor it. That's a guarantee it's going to be no solution, but for remembering for future classes or for anyone else watching this, you should always confirm your discriminant is negative before you definitively say no solution. We've certainly factored numerous quadratics that have numbers in front of squared terms. We just did them with the partial fractions. So always confirm the discriminant is negative before you go ahead and make that kind of assumption. All right, so that's it for Unit 9. Next up, Unit 10 is going to talk about polar and parametric equations. So again, to it's for those videos. So I'll see everyone next time.